Printing is done on rotary machines, flatbed machines. These flatbeds have big, very big screens which are put on top of the fabric, and then these are very similar uh, to the printing that is done in small cotton industry, where we have small screens, rectangular screens. We put it on top of a certain segment of the fabric, and then we roll over the blade on the die, and then it does the printing. Then we have digital printing as well, which is slower process, high precision, but very slow. Then the pigment printing or reactive printing both require curing, and both require curing around or above 100 degrees Celsius. This curing process is pretty similar to how the heat is provided in the stanter. So thermal oil goes through heat exchangers, and through heat exchangers, while going there blowers that heat up the air inside, and then the curing, this dry curing is done. If we have reactive printing, then we also have to have washing afterwards. And in this case, curing is done in a moist environment for reactive printing. In pigment printing, it's done in the dry chambers, and in reactive printing, it is done in the moist chamber. So this is how it is done. So it is air heated, and automation of curing chambers can be done by linking the temperature required. So if we monitor the temperature, and then we automate the fans speed with it, or if we install or solenoid valves, high temperature solenoid valves with the thermal oil heaters, and we bypass thermal oil, or we simply stop intake of thermal oil in that certain chamber. That is how we can also reduce intake of energy. Then heat recovery from exhaust flue gases can be done, and insulation of curing chambers. These are three main energy efficiency options in the printing machines. Then in finishing, we have chemical and thermal finishing, as well as we have mechanical finishing. Chemical thermal finishing is done usually on stanters for continuous fabric rolls, and mechanical finishing is done on calendars, comfort, or sulfurizers. And indirect heating is also used in these kind of processes. I'll discuss stanters here. So energy efficiency options for stanters are actually modulation of thermal oil heater, or if we have natural gas burners, for example, then we need to measure the temperature inside the chamber. We need to set a maximum or minimum temperature as well, and then we modulate accordingly. For the oil heated stanters, I had a discussion with Allplan, who are suppliers of oil heaters. They recommended to heat up oil to 50 plus degrees compared to the requirement of the stanters. So if we need 150 degrees Celsius temperature inside the stanters, the oil should be heated up to 200 degrees Celsius. What I have often seen is the factories are heating up oil between 250 to 200 and 300 degrees Celsius, and the processes are using heat from 120 to 150 degrees Celsius. That means we are putting in too much energy in heating up the oil. And this we can see at the oil heater. So when we go to the oil heater, the outlet temperature is 300 degrees Celsius, and the oil that is returning from stanters is coming at 295 to 96 degrees Celsius. So only 3, 4, or 5 degree delta T is gained inside the stanters in this case. So a usual recommendation is that we should heat up the oil only up to a level where when the oil returns, it at least has dissipated 8 to 9 degrees Celsius of heat. So that can be achieved if we have an oil heater running at 200 degrees Celsius. Oil goes into the stanter, heats up the stanter up to 150 Celsius, and returns back at around 190 and to 193 degrees Celsius. That is when we can optimize the thermal oil as well. There was a question earlier. I hope everybody knows this. Q is equal to mCp delta T formula, right? So Q is energy So Q is energy, M is mass flow, Cp is the specific heat, and dT is the temperature difference. So let's assume that we provide hot oil. So Q is the amount of energy. We want to know how much energy is being consumed by a stanter. M is the mass flow rate of the thermal oil, and this we need to estimate, which we can try to estimate from the pumps that are pumping oil towards that stanter. So you can there are usually pumps which are pumping oil towards the stanter, and that is where we need to estimate it. So this needs to be estimated from hot oil pump data. Specific heat, we need to know which type of oil we have, and we need to have a Cp for specific thermal oil we are using. And then we see T1 would be the temperature of oil at inlet to stanter, and T2 would be temperature of oil at outlet to the stanter. So for dt we need T1 minus T2, because T1 would be higher and T2 would be lower. That is how we can calculate dt. And if we put them all into the right units, we can calculate the amount of energy that is going into the stanter. Now, if we want to shift to natural gas, we know how much energy we need here, right? So Q we need in this, we calculate Q above. In this case, that was Q provided by oil, and this is the same Q that we need to for from natural gas as well. So natural gas should also provide the same Q. So let's say it's Q1, that is, it should be equal to Q2 provided by natural gas. And from here, then we need to calculate the mass flow rate. So this time we're going in opposite direction. We know the specific heat of the natural gas. The next point would be the temperature difference. So in this case, we might need to do a calculation inside the machine. So how much temperature do we want to gain inside the process? So for example, we say that our air enters, in this case dt we need to calculate. So in this case T3, that is the temperature of the air, is the air that fresh air or intake air of stanter, and T4 is the desired temperature of the air in stanter. Okay, so this is where we get the dt this time for the natural gas usage, because natural gas itself does not heat up, so we need the temperature of the air inside in this case. And this is by backtracking, we need the Cp2, that is Cp of natural gas in this case, because we're putting natural gas. So the M would be, M is equal to Q divided by Cp dt. So this way we calculate the amount of natural gas required. Or there's another way, since we know the Q value, let's say this is in 1000 MMBTU, then we know the GCV of natural gas. So we could directly see how much amount of natural gas is needed to provide this amount of energy. So this would be even more direct method. Sorry, I think this is an indirect method that I showed earlier. but this is a more direct method. So we have this Q that is needed inside the process. We know how much it is, and then based on the GCV of natural gas, we calculate how much natural gas would be required to provide this. Obviously, for this, we also need to know the efficiency of burner. So whatever value we get here, we need to account for in that efficiency of burner, and then we get the actual input. So for example, let's say we say that 1000 MMBTU of natural gas is required. So we would need, so we say 1000 divided by, let's say the burner is 60% efficient. So 1000 divided by 0.6. This means we need 1666 MMBTU of natural gas required. So this is what can be converted into cost. So this amount in MMBTU can be converted into cubic meters and then converted into cost of natural gas. On the other hand, we also need to see how much oil was costing here. Okay, so let's say if 1000 MMBTU was being provided by oil. So, and this oil was being heated by coal. Okay, we know that usually these oil heaters, which run on coal, have an efficiency of around 75 to 80%. Let's assume 70%. So efficiency of oil heater is 0.75. So energy of coal needed would be, in this case, 1000 divided by 0.75. So coal needs to provide 1333 MMBTU of energy, right? And for that, we need to know the GCV of coal. So GCV of coal is needed. And based on this GCV, we can convert it into ton of coal and then multiply by the price of coal. So this is what we do with the coal, and this is what we do with the natural gas. So if we have 1,666 cubic meter of natural gas, then we convert to price of natural gas, and then we can compare both of these. Usually the standard working on natural gas is cheaper because it has less points of inefficiencies. So I will just remove this one because this is causing troubles. Just forget it. Okay, so I will repeat that first we need to calculate the energy that is being dissipated by the oil to the machine. And if we are using the temperatures of oil, this way we are already accounting for the inefficiencies of the heat exchangers inside. So there we are already good with it. Then we need to calculate, backtrack, how much coal would it be required to heat up this amount of energy in the oil heater. And for that, we also need to have efficiency. On the other hand, same amount of energy has to be provided by natural gas. We need to have efficiency of burners. In this case, we convert it into cubic meters of natural gas and then we multiply it with the price. We can compare both of these together and see which one is better. In this case, for example, in case of oil, we have inefficiency of the oil heater. Then we have inefficiency in the transmission. We have inefficiency inside the machines. That is inefficiency of the heat exchangers. So there are 3 or 4 inefficiency points. A lot of points where thermal oil heat can be dissipated to air. In this case, we are directly doing the burning inside the machine. So we have at least 2 less points of inefficiency. At least the transmission inefficiency is not there. So this way, usually the natural gas stentors are more efficient. Now so there are normally 2, 3, or 4 heat exchanger points. In some stentors, we have even 8 or 9 chambers. So for each chamber, we have heat exchange points. We can either calculate separately for each of these, but before and after this stentor, we have distribution points where the oil is getting distributed. So at the intake of this, there's one small header which distributes thermal oil to the multiple chambers of the stanter. So we need to measure the oil temperature before this header where it is further divided. And then when it goes back, it again, when it comes out of all these chambers, it combines into one line afterwards. Not all the lines go all the way towards this oil heater. They all combine into one line afterwards. That is where we need to calculate the temperature. So that is how we calculate the overall delta T. But however, when it comes to mass flow rate, that is where we might need to calculate it separately as well. If we have pumps inside attached to the oil pumps attached to the stanter, then we know the mass flow rate there. And if we don't have pumps of the stanter itself, but we have pumps only at the oil heater, then we take overall temperature T1 and T2. But if there are pumps attached to the stanter itself, then we need to measure the quantity of energy and flow rate for each pumping separately. So we can consider one pump as one quantity center, as did in the material flow cost accounting earlier. Calculate energy required separately for each of these chambers and then merge them together. So automation of stanter can be done. So for stanter, we can have waste heat recovery from air as well. So what the air that is going out, it can be, we can install an air to air or air to water heat exchanger, depending on what is required. Usually I recommend air to air heat exchanger because it is easier to handle. Installing an air to water heat exchanger a little bit more tricky, because then you need bigger heat exchangers and you need more piping. If you just install an air preheater, that provides more direct benefit. So this is an actual case. So the exhaust air flow we could not measure because there was no area of measurement. But in this case, we did some estimation based on the size of stanter, the size of exhaust fans, and the amount of vanes or ducts opened. So we did some estimation here. We knew the exhaust temperature of stanter was 160 degrees Celsius. We wanted to bring it down to 100 degrees Celsius. So delta T was 60. Operation hours were 7,200 hours a year. And the specific heat was for this air, because this was running on thermal oil. So we don't have a flue gas in this case. We have just hot air, and specific heat is usually 1 in this case. If we have a burner installed that is for natural gas, then we need to use specific heat of flue gases rather than specific heat of common air. So just remember that you need to change this value in that case. Then available energy was calculated using Q is equal to mCp delta T. Cp is 1, delta T is 60, and m is 2.45 kilogram per second. Then we had a look at this was our available energy, kilojoule per hour, 529200. And we knew that our thermal oil that we're providing, we have an overall efficiency of 70% there. So we actually use that efficiency to calculate total recoverable energy. Sorry, we use the efficiency of the heat exchanger in this case, how much we could recover. So an air-to-air heat exchanger usually comes in with a 70% efficiency. So we saw how much can be recovered and how much it would save coal, considering the 75 to 80% efficiency of the oil heater, which is providing heat here. So this amount of coal was then multiplied by the coal value, converted into the financial saving. Investment for this kind of stanter was 25,000 USD. The saving after deducting all the operation and maintenance was 17838 USDs. A simple payback is 17 months. And this amount of coal accounts for 298 tons of CO2 emissions. So it's simply using Q is equal to mCp delta T, and then using the efficiency values to come to a realistic amount of recoverable energy in the heat exchanger, and then also using efficiency values of the oil heater to come to a coal value. And then that is how we can calculate the financial savings. As you can see, the payback period is 17 months. We could also calculate IRR in this case, which would also be very, very high. So definitely a very, very feasible measure in this case, except for small or medium companies, which usually anyways don't have stentors, who think that they do not have enough money to apply. This company I'm talking about had 28 stentors, and they could apply it on every stentor. And they had one stentor which already came with this kind of heat recovery unit. So I did not have to convince everybody there. However, they had one utility manager who had, I don't know, many apprehensions in mind, but these were actually just fears that he had. So we had a discussion of 15 minutes. He had some technical questions, just like you asked on the previous slide, and he was pretty much convinced. And now they're going forward with the procurement as well. I have seen this working everywhere. Perfect energy saving opportunity actually. I hope you all remember the case of textile company, which had exactly this process. We have yarn dyeing. So yarn is converted into a rope, then it is bleached, washed, dyed, softener is applied, and sizing is applied. Then this sized yarn goes to the weaving process, which I have not shown in middle here. And after weaving, it comes to singeing. And as I told earlier, that inside the singeing machine, we also have a desizing process, after which we usually do mercerizing. And then we do stentor for the control of fabric quality, fabric surface, as well as its shrinkage is, and fabric size, width is controlled here. Then when we go to garment making, sometimes this fabric, if it is sold as fabric after the stentor, some companies also applied size here. So sizing process also comes here sometimes. In which case, when we go to garment making, we also have to do a desizing process there. So this desizing process sometimes is done before cutting, and sometimes it is done as part of the washing process, usually as part of the washing process. So there we have cutting, stitching, washing. In washing, we have multiple processes. Then we have drying process. Then we have distortion or special effects, and then steam pressing and packing. These first two boxes, yarn dyeing and denim fabric finishing, the process parameters are quite similar to what we have seen for already in the previous slides. Just that the formation of machines is a little bit different sometimes, but the process parameters are quite similar. And since we already had a detailed discussion on this process in the textile company as well, where I already explained this process inside the story as well. So you can read that. So for denim, when we have done the stitching of denim, it comes towards the washing process, where we have desizing. So there are normally two types of washing machines. You can see on top there is a barrel washing machine, which is more of a manually controlled one. In the bottom we have an automated or semi-automated machine, which has all the automatic controls there. The barrel washing machine consumes more energy, consumes more water, and washes less garments. But it is easier to do dyeing in barrel washing machines. So process usually is in a way that in one machine we load the garments, then we do desizing. So desizing, rinsing, bleaching, then we neutralize the bleach. After that, we do the stone washing, then we do the rinsing again, so that all the effects of the stone abrasion are gone. After that, the fabric is unloaded, the garments are unloaded from the machines. They are sent to the drying process, where we have steam going into the heat exchangers, but this is a dry process. So steam goes out as condensate, air is dried, air is heated up with the steam, and the whole system is dried. Some dryers also are run on natural gas sometimes, but these are old technologies. After drying, there is KMNO4 spray that is done on the fabric. Then we again send it back to the washing machines where this is neutralized. After neutralizing, we again have sometimes stone washing. Then we apply softener, and then we again apply drying. So this is a usual common process for a cotton simple jean. If we have fashion elements, then we might have other inside processes as well. So this can be divided into mechanical processes as well as chemical processes. So mechanical processes are rinse washing, water jet fading, stone washing, whiskering, micro sanding. There are some sandblasting machines as well, which are used. Mechanical abrasion is also used. Then we've often seen laser machines being installed, which are replacing a lot of finishing processes as well as KMNO4 application. Chemical processes are acid washes, sometimes ice or snow washes are also done. Hydrogen peroxide washes or bleach washing is done. Enzymes are applied. Ozone fading is applied sometimes. But this laser is now taking place of ozone as well now. Then there are some spray techniques where the softeners are sprayed. And sometimes over dyeing and tinting is also required on some of the garments. There is this document called Levi Strauss and Company Waterless Program. This document provides many options of improving water and energy consumption. This is mainly targeting water consumption, but also we have seen big energy consumption here. So if we, for example, in stone wash, we reduce the water quantity by half, we can get average water savings of 2.5 liters per jean, and the steam also gets half because we have half stone bath in this case as well. But this can not be used on every kind of denim. So critical issues are that back staining can occur if we are using less water. Low liquor ratio stone wash is very difficult if we have belly washer machines. Belly washer machines are these ones on top, this barrel wash or belly washes. In here we cannot use low liquor ratio, and it is not recommended to use a liquor ratio below 3:1. So 3 is kg in garments and 1 is kg of water. And because there are new advances in enzymes and dispersant chemistry, so this technique is becoming easier now to use. But this back staining is a big issue to be controlled. Then combining some processes. So you can see traditionally we have a desizing, then rinsing, then stone washing, and then rinsing. So this one rinsing can be removed. So soon after desizing, we can do in the same bath of desizing, or in a separate bath after desizing, we can do a stone wash, and then we can do a rinsing. So removing one rinse would mean that removing water quantity, about saving 800 liters per batch of water, and saving equivalent amount if the rinsing is done hot or cold, depending on that. So there's big water savings and big savings for 2 baths which are being removed. The method is that when the stone or enzyme wash is followed by a desize bath in the finished formula, it requires 4 baths, but then we combine them, the desizing and then stone together in 1 bath, and then we have only 1 bath for desizing plus stone and 1 bath for rinsing. So normally 1 bath takes up to 800 liters of water. So if we are saving 2 baths per batch, that means we are already saving 1600 liters of water per batch. You cannot use it with the fabrics that bleed a lot. So if you have dark indigo color, you have green colors, you have this kind of colors which are fast colors and they bleed a lot, never use that. Some extra dispersant also needs, because otherwise if you don't have a dispersant in the water, it would actually do some back staining as well. So some trials need to be done before doing it in the main machine. It's always better to do these trials in the product development section on small trial machines, and once we are successful there, only then we can do it in the main machines. Then if we, for example, ask the fabric mill to provide the fabric without desizing, then the desizing bath can also be removed. This is usually possible for the factories who have their own denim mills. They usually then do not apply size after on the finished fabric, and they can directly send it to the cutting, stitching, and then washing process, so they don't have to do the desizing. So there are different other options. I won't go into that detail. What you can do is that you can have a look at this document of waterless dyeing, which tells us which of the processes can be combined with which processes. So green box means that these processes can be combined together, or the savings from these can be combined together. And red means that these should not be, the savings cannot be combined. So if we are removing desizing step, for example, we must not combine the enzyme wash with desize, or we must not combine desize with stone wash. This is what cannot be done. Or if we are using spray softener, we cannot use the soft rigid process, and we cannot combine the fixing and softening, because the softener has to be done separately. So these are some cautions that need to be done. The green areas are which we can easily apply in combination. Do read this document in your free time. Then the drying process, we have a modulated steam pressure coming in. There we have process temperature requirements. We need shade of fabric. We need to look at fabric weight, batch size. These are the variables that we need to look at to optimize the steam use. Some companies do not install even the pressure reducing valve. So whatever pressure is coming from the main header goes into these machines. So we have seen often that we provide too much steam, which actually at the end deteriorates the heat exchangers as well as deteriorates the pressure, the condensate returns or the steam traps. So we need to control the pressure of the steam. We need to modulate it based on the temperature in the machines. And we also need to keep an eye on the steam traps, if they are working properly or not. If the steam traps get stuck, we get too much back pressure. If the steam traps stay open, the steam consumption increases. So it is very, very important to keep an eye on the heat exchanger and to keep an eye on the steam trap to run this process smoothly. There's another option which is coming in new machines, but it can also be done in a retrofit. That is, we can recirculate the exhaust air. Since the exhaust air is coming in from one side, going through the heat exchanger, heating up the process, and then from these red ducts is going out. We can install a bag filter here to save money instead of an electrostatic filter, and then recirculate a certain percentage here, also adding some fresh air, probably 30 to 40%, just like we do for the carding machine filters. And then we can have a better heat exchange because the air would already be hot. So we'll have a quicker heating process. This is now coming in new machines already. It's a pretty simple process, just have to do, but recommendation is to do one trial, probably do one trial on the product development machines, and then you can use it on the main machines. Then the blow cleaning process, we have this abrasive process usually. So we do this cutouts, this with the razors or blades, and then we have to clean the weft. To clean the weft, we use high pressure compressed air because it cannot be cleaned by the brushes. If the video runs, you can see this is the way they do it. And usually I've seldom seen them using a pressure gun here. So normally they combine 2-3 pipes together to have a big volumetric flow. And then you can see that they just blow inside. And the pressure is very high. It is difficult to handle. A lot of air is leaking. So this is one reference calculation. So this process has combined 3 pipes of 4 millimeters together. The air consumption per station was 94 cubic meters per hour. If we install a gun, reduce the pressure, to required pressure, we would have cost saving of 6,000 USD per station. And if you go for an electric blower, for example, the investment is only 500 USD. So we could, instead of using compressed air, we could just go for an electric blower, and that would save a lot of money, and we would need smaller compressors as well, and the return on investment is immediate actually. So this is something that can be looked into. There are new equipment also coming in, which are actually some these chambers where you load the machine into it, and it has blowers inside rather than compressed air, and it does the blowing inside the chamber, exhausts the fluff outside, and then you take the denim out. The problem is the investment is a bit higher, and obviously you need to have some practice of using it, but it's not rocket science, it can easily be done. But obviously, at least what we can do is to control the pressure here, of how much pressure do we actually need, and also have gun there, because this is leaking continuously. Talking about cut to pack, we have the processes of pattern making, cutting, stitching, and packing. It is more human resource intensive process, where lighting, ventilation, drinking water is required, thermal comfort is required, where we need some cooling or we need heating in the winters. That comes along with the ventilation system, but generally electrical energy is needed for stitching and for compressed air in these cases. So process optimization is very important in this case. If you see this cycle time analysis that we did for a factory here, so this bottom stitching had 4 further steps. So what we did was that this one person was doing the bottom stitching, and we made a video of multiple processes he did, and we divided his process into 4 sub steps. In the step 1 ranged from 9 seconds, went up till 14 seconds. Step 2 ranged from 1 second to 12 seconds, where average data was from 3.25 to 5 seconds, and average cycle time was 4 seconds. Step 3 again had big variance. Minimum or maximum values were 9 seconds and 19 seconds, but average variance was 1 second. Step 4 was the process which had highest variance, that on average the lower value was 3 seconds and on average higher value was 7.5 seconds. There was 1 or 2 exceptions where it went up to 27 seconds because of thread breakage. And in total, when we had a total cycle time, the variance was from 25 to 53 seconds, but the average variance was of 3 or 4 seconds. This variance looks small in total, but if you have a look at process number 4, that is where this can be improved. If we improve this, we can save 1 or 2 seconds in total cycle time, which amounts to a huge production improvement, productivity improvement. This in terms, we have seen that 8 to 10% variance of process time can be seen. If we bring it down to 4 to 5% of variance, we can save huge amount of electricity, compressed air, as well as can improve productivity. Second option is to install servo motors. Most companies have now already installed servo motors. In this slide, I provide you one example measurement that we did for clutch operated motors and servo motors, where the payback was calculated. So 60% of the cycle time was loading time, that is the needle was doing the stitching at that time, and 40% of the time when we did the observation and made the video, the needle was not doing the stitching. For example, the worker was changing the direction, or the needle broke, or the fiber broke, or he was changing the point where he had to do the stitch, for example. And we saw that the clutch motor on load was taking 0.6 kilowatt load, and off load it was taking about 33% load. On the other hand, servo motor was taking 0.5 kilowatt during the load, and off load, I think this load came from its panel that was consuming some electricity, the automation controls or control panels, 0.02 kilowatt load was there. So based on this and based on this 7,200 hours of annual operation, we calculated how much energy would be saved if we switch from clutch motor to servo motor. And this is the calculation shows on load for one machine, we save 475 kilowatt hours. Off load, we save 602 kilowatt hours. And in total, we save 1000 kilowatt hours annually only on one machine. Imagine a factory having 100 machines or 500 machines or 1000 machines, how much energy they can save. And this is only electrical energy. Because of this, we would also save some compressed air as well. So that would also add to it. One example, 2 points that can be done in the stitching process apart from lighting or the savings in compressed air in general, that we can install servo motors or we can do some process optimization as well.